Welcome everyone to the class today. Um, in the last class, we learned about models of agent-based models of collective behavior, collective emotion specifically. And the features were as follows. They were agent-based. We were trying to model every agent, right? They're also sometimes called individual-based models. And another feature of it was spatially explicit. Okay, so unlike mean field models, here you really accounted for where the individuals were in space. And of course, there was also stochasticity in them. And the models we studied were modeled by Richard and the other one was by right? And then we discussed the idea of emergent properties. Okay. We discussed the idea of emergent properties and in the context of collective motion, and I gave some examples of this, how to make inferences about group behavior or to characterize the group behaviors based on the observations that one. So it was done using the examples of empirical data. Right? And we looked at examples of two examples, I think. I think starling flocks. And the other one was if homing pigeons, right? Any questions before I go forward?
Yeah, I had a question from last class.
Sure.
So in the starling flock, when we looked at the spatial correlation, there was some monotonicity, I guess, because sorry, non-monotonicity, because the correlation went, the speed correlation went down and went up. So why would that be the case?
Oh, you mean this, right? What you actually mean is that the following, right? You plot the correlation function with a function of r distance, right? And then you found that it would do something like this, right?
Yeah.
The correlation function, the spatial correlation function declined, became negative also, and actually then came back, right?
Oh, so the orientation became negative. I think the speed was still positive, and then again it increased.
This was orientation.
Yeah, orientation it just went negative.
I have to look up. I don't remember. Suddenly, this happens for I think orientation. You're asking what happened with the speed. So I don't remember the results of speed right now. So you're saying it does something like this?
Yeah. In the slides you showed last week, it did something like that.
Okay. I mean, I can only speculate because I haven't analyzed the data directly myself. One possibility is that this might be, see, the largest distance, right? So the largest distance typically corresponds to, what can you just, if you have a flock, what is the maximum distance possible between extremes, right? So the extreme individuals who have, who show largest, who are at the largest distance. There are two possible reasons why this behavior might be there. I can only speculate. One is it's entirely statistically spurious. There's really no pattern there. It might be effectively still equal to same as 0. That's the one possibility. If it was significant, the one reason I can think of is that the individuals at the edges are the ones who change directions, right? Are likely to be changing the direction first. So it's possible that they actually have to move faster to stay in the group because, if there's a rotational motion like thing, right? So possibly they may have to move faster is one sort of, speculation I have. So but I can't be very sure because, I myself haven't quite analyzed the data. So I suspect something has to do with the edge effects, I suppose. That's something one can sort of speculate. Any other questions? Okay. So if there are no questions today, we will do a small work. Okay. Okay. Let's sort of try to sort of learn some more models and also some work, some revision. Okay. So let us. So I have a very simple minded problem now. So now, as you can see, there was, just think of the following broad question. Let's say, so let's say if you now observe some grouping animal, okay. Okay, so you have the some best, we have some data from these observing grouping animals. Okay, now let's ask the following question: which model best represents data that you collected? Okay, now this is a question, if we have done all these modeling work, right? And if you now go and talk to an empirical person, and this is what they will say, they're going to have studying this, a bunch of beetles, or maybe swarm of worms, or maybe bacteria biofilms, whatever it is, Now tell me, does your model fit, or can you build a model for this, right? So I want us to think a little bit about how would you go about this, okay? Because this is actually quite a non-trivial problem, okay? Now it really depends on what are you trying to observe, what are you trying to explain with the model, right? When somebody asks this question, okay. So in some sense, what those two models I described to you, what they did was they sort of they started off with the broad inspiration or motivation by observing the natural world. We see all these birds of flocks, flying synchronously, moving, swirling, and so on. And we see these, swarming behavior in so many different species. What is a very simple model that can explain these type of grouping and group movement, right? So that's the broad motivation. And when those models were actually written down, I don't know if they had a very specific phenomenon that they were trying to explain. They were trying to broadly explain that, some observed group level phenomena. Right? That's what they were trying to do. And that's what usually a lot of modeling exercises are. Usually, even for example, much of the models we do are on in that spirit, right? I want to build a model of population, and we come up with, let's say, a population logistic model. Okay, now I want to incorporate, and we realize in the process we have incorporated these processes, right? For example, logistic model will only have intraspecific competition. And now if you think of, let me try to model a population which has some positive feedback, we will now model differently. Now again, when doing so, you again think of some simple features of positive feedback and incorporate them. And probably will get different set of equations. Now let us say somebody now comes with data, and the person is willing to collect data for you. Now, how will you build a model for that, those type of systems with data? Now that's actually not always a very easy problem. Okay, so now that's the question that I try to address in the next couple of classes. Okay, and today we will make a first effort. We will not complete this problem at all. So, what do you think is a strategy would you adopt to address this question? When would you even start thinking about this problem? How would you go about thinking this problem?
We will first visualize the data.
Visualize data. Okay. Fine. Okay. And then
Um,
visualize plot in various ways, right?
yes, and if we can get some statistics out of that thing.
Uh-huh. So, it really depends, yeah, various ways, right? Construct some statistics, right? Plotting will involve some constructing some statistics, I suppose, right?
We can try to find some sort of parameters which are mappable, right?
Find
Like-
some parameters.
Like say if we can predict the velocity from the model and then we can map it to the velocity which is there in the data, something of that sort.
Parameters to model. Okay. Okay, fine. What else? What else would you do?
We sort of also will have to be careful, like, I mean, if it sort of overfits the data. So,
It's the data.
so I
here-
mean, we should have minimum
say-
parameters or something.
Okay. You minimize the number of parameters. So here is something we missed in the process, right? We visualize and we plot something, and we're all talking about fitting and overfitting and so on and so forth, right? Here is the question: what are you fitting? What are you fitting to what?
Model
You're fitting model to what?
data.
What does it mean to say I fit model to data?
So, I mean, we can have some quantity like say, I mean, say correlation length, which we can get.
What
I
does
mean, some quantity which we can get from the model and from the data as well. So, and then sort of plot that and then try to fit it or something of that sort.
Can you just repeat what you said? I'm sorry.
So I was thinking we can find a quantity that we can get from the model, and we should be able to get that quantity from the data as well, sort of by some calculations and stuff, and then try to fit it to different parameters in the model so that we can get an idea of what parameters, what are the ranges of parameters which of the model which will fit the data.
Okay. So let us think of, let us ask this following question. Okay. We had homing pigeons that we looked at, right, last time. We had this homing pigeon data, right? That was the question, that was the data we had. Okay, now you are saying you will calculate something from it. Can you give me an example? What will you calculate? Something that we did not discuss last time. It has to be something different from that hierarchical structure that we discussed last time. Okay. Anything else? So what will you calculate from this?
Maybe average distance between the pigeons or something of that sort.
Let's call that quantity 1. Let me call that, denote that by Q1. It is the average distance.
Yeah, between the pigeons and as a function of number of pigeons or something of that sort. Maybe, yeah, I mean.
Okay. And you plot it as a function of number of pigeons in a flock.
Yeah, and then from the model we can get this quantity, if we can get this quantity.
Okay, so that's good, that's useful. So you want to know, so basically, if it assumes that in the pigeon data there were many different flock sizes, right? And you look at, let's say n is the flock size, and then this is Q1, right? And then you plot this. Is that what you're saying? Okay, and then you get some pattern.
Yeah.
Could be a pattern, it could be a decreasing pattern, or it could be
Decreasing or
increasing and decreasing, or it could be
could be non-monotonic. Yeah.
This could be any of this, at least
Yeah.
4 patterns you can think of, all the 4. And then what do you do after this?
then you sort of calculate the same quantity from the model, and then try to see what values of parameters give you the behavior close to it, sort of by via linear regression or something.
Same, not we say the same whatever relationship. It's not a quantity anymore. No. So I
Right,
think
right. Yeah. The relation. True. Sorry. Yeah, but-
in various models, right? Is that what you will do now?
True.
Excellent, very good. And then see what works, right?
Yeah.
It's closest to data. Excellent. Is everyone in agreement this? Any questions on this? So you calculate, this is really good. So you calculate something like average distance between pitches, and then you do it for different sizes. So into something, one can, for example, we discussed two models, right? For our collective motion last time. We can do this quantity, the relationship for both the reject model, cousin model, and we can look up the literature and maybe look for two more models of this type and see what all do they show, right? And then see which of them is is closest to data, right? Okay. So and then you will find out that some model is closest. That is one possibility. For example, all the four models you consider may actually produce this kind of four different patterns, and only one of them will then be matching the data best, right? That is one possibility. What else can happen when you compare data on models? So ideal scenario is, each model 1, it gives you relationship 1, model 2 gives you relationship 2 and 4 and 5, right? Different models give different relationships, and then look at what is the data, what is the relationship within data, right? That's one, and then do you see the best fit? What are the other possible scenarios that can happen?
We get similar relationships from different models.
Different models all show same relationship. In that case, what can you do?
So if that is the case, so then we choose this model with simplest assumptions.
Okay, that's possible. Okay, but it doesn't mean it's correct. It's a correct model, right? Animals might be still doing very complex things, right?
Yes.
Why would you choose the model with simplest assumption in that case, right? Unless your question is, okay, I want the model, the simplest model that produces such a data, right?
Yes.
Yeah.
So I have another question. So having the data, can we say that, okay, so this is the complexity of the data, or say, so how to what levels of complexity should we go with a model? So if we have some data, so how do we decide that?
That's also, there is no easy answer to that question. Okay. So now, before I even answer that question, let's just give a real example here. Okay. So, Vichek model, for example, makes a very, by the way, before I ask this question, okay, here is something, right? One way to go about these kind of modeling and data integration is this, right? I decide to calculate Q1, and then as a function of some variable n in this case, and then I look which model produces the closest answer. What's another way of doing it? Which is probably what happened in this field specifically, is that models first made predictions about various quantities. For example, Vichek et al., they make the following prediction. So what they do is, if you look at the group polarization, let's call that P. I think we defined this last time. Let's call this N. That's what, right? Where M is basically summation of the orientation vector of all the individuals divided by N in the population. Okay. And then if you plot this as a function of density, it actually makes this following prediction. It will look like this. What it basically, I mean, of course, the simulation data don't look exactly like this. It shows slightly more smoother curve for small groups like this. But it basically shows the following: for up to some critical value of the density rho c, the system actually has low or no order. We call them disordered flocks. And then you have the order sets in a flock. So here, of course, a flock is not a single unit. By the way, it's the entire population. The M is calculated for the entire population that you see in your simulations. Okay, this is the prediction that this model actually makes, which checks. Oh, what is this? I have to kill this. That is the prediction that actually this model makes. So therefore, if you are an experimentalist, what will you do now?
I can sort of calculate the. I mean, if I have the data, I think if you have the coordinates and the time points, we can calculate the polarization, right, as a function of density for different Hertz or something.
Absolutely, yes. Okay, and then you see what really happens. Okay,
yeah.
That's why such an experiment was actually done, with locusts. There is a paper by in 2006, and let me see if I actually have a paper on. So I can even show the graphs they found. Excellent. Because let me stop sharing this with. I'll share my video. Okay, this is from disordered order in marching locusts. Okay. Okay, now here is the thing. Okay, this is what they find. So you should read the paper if you want to understand exactly how it is set up and so on and so forth. But this is what they find. This is exactly the same quantity we are talking about, analogous of that. Okay, what they find is, I think this is actually simulations. Okay, which is an Wittek model but adopted to experimental conditions. So experiment has some arena size, right? It will have some physical boundaries and so on and so forth. So what they do is they take the Wittek model and adopt it to somewhat realistic experimental settings, and then they find that if you increase the density from low density in this case to intermediate density to high density, you find that the instantaneous alignment. Alignment is basically the M that I mentioned. It's a measure of alignment that is fluctuating, but is closer to zero for low densities, and for high densities in C, it actually is now basically at 1. It's always very high. 1 is the maximum value you can take. But at intermediate density, something interesting happens, which is that it goes back and forth between value of +1 and -1. To understand, I hope they have given the experimental setup. They haven't. The experimental setup is actually not a two-dimensional world that I showed you. The experimental setup here was actually an annular arena. It's more like, think of it more like a ring, but where the ring, one-dimensional ring in a mathematical sense, but the ring has a finite width. Okay, which means that in that width animals can move, the locusts can move. Okay, so basically 1 would mean everybody is moving in the clockwise direction, -1 would mean everybody is moving in the counterclockwise direction. Okay? So that is what is happening here. But this is all model. This is all adaptation of Wittek model to such an annular arena. If you remember, Wittek model that I showed on Monday was the two-dimensional continuous space, right? There is one-dimensional, effectively one-dimensional continuous space, okay, in an annular arena. Is it clear to everyone what an annular arena would look like? How would it look like?
No, not clear.
Not clear?
Yes.
Okay, maybe I'll just draw it. Can I draw it here? On this, if I can draw it. Oh, I can't. I don't know if this is a drawing tool here. Maybe I'll draw it on the OneNote. Okay. So imagine something like this. Okay. Animals can't go here. Animals can't go here. They are, this is all prohibited area for animals. This is a wall. Okay. This is a wall here. There's also a wall here. So animals can go only this way, and this is sufficiently narrow channel that they really can't do too much of this, radial motion. They basically can pretty much do only angular motion. Okay. That's what is happening. Is it clear now? And if everyone moves, let's say in the clockwise direction, that phi that they were plotting becomes -1. If everybody moves in the counterclockwise, phi will be +1. And if individuals are moving randomly, half of them will be in one side, right? Clockwise. Half of them will go in the counterclockwise. In such a case, what happens? Phi will be close to 0. Is that fine?
Just one doubt.
Uh-huh.
We are assuming the collisions will be like resolved without any issue, right?
What do you mean by resolved without any issue?
Like when a group going in clockwise meets counterclockwise.
Yeah, you would imagine that animals know not to collide.
Okay.
I mean that is incorporated in the model. So basically, when I said that Vichek model was adopted to this kind of an experimental setup, they incorporate these kind of additional rules. I think the exact rules are there in the paper.
Okay.
But the main thing they do is in their simulations they actually assume that animals move now only this kind of an angular region, and they incorporate the dimensions of the experimental setup and all in that. And they also assume speed and other quantities which are comparable to actual experimental system that they are looking at. Okay. I'm not very sure if the model that they actually accounts for collision though, but of course the real animals will avoid collisions. So is this clear now? What is annular arena? Then I'll go back to the paper.
Yeah.
Okay, excellent. Okay, so now that you know what is this phi, right? So fluctuating around 0 means that most of them are sort of going in a random directions, and at least there is no entire group level cohesion or alignment. Therefore, it's around 0. -1 to +1 transitions mean that they are all going in one of the angular direction. Either let's say one means counterclockwise, and then suddenly every one of them, by the way, switch to clockwise direction. -1 means clockwise. Okay. And then again, suddenly every one of them collectively switch to counterclockwise, and so on and so forth. So this is something like in some sense alternative stable states. Okay. That we studied in the context of ecosystems. Switches between two alternative stable states. Collectively, the entire system is changing, but this is happening over a very, very short span of time, just a few hours. Okay. And this is the high densities. You basically expect that they will continue to move in the same direction. And the animals could have picked +1 or -1 equally likely, but once they have picked, they just stay there. They don't switch anymore, like the intermediate density case. So is the model predictions now clear? Okay. So let us see what the experiments actually find. So they do experiments with locusts, which are grasshopper species. So this is again the analogous figures, but with real data now. Okay. So this small number of only 7 fish. Okay. And the A is 7 fish in the arena, B is 20 fish in the arena, C is 60 fish. Okay. So and as you can see, because the area of the arena is context, density is increasing as you go along this axis. So they show highly disordered for a large part. Of course, there are some parts they do become ordered, but again, if you compare across A and B, you will see that the ordered time is higher, but there is a switching between +1 direction and -1 direction, which means counterclockwise and clockwise. And exactly as the model predicted, they also again find that when the density is very high, you just stick to one of the two directions for a very, very long time. Is this clear? So this is an example of trying to sort of make connections between real data and experimental data. So you have a prediction from the experiment, prediction from the theory, okay, and then you test them out in the experimental system. That's all. These are probably more. You can read the paper more. I think more about some connection between data and experiments. Okay, but this is the main point of it. Okay, so now let's go back to further discussion on this. Okay. So this is how you sort of think about connecting between data and models. What else? What else can you ask? This is similar to this Q1 that one of you suggested, right? Measure some quantity, it's average distance. It was just that the Q was different. It was M. We just measured average polarization as a function of density. Right? So it was a different quantity. What else what else does it mean to say that we test models? There are two ways to ask this question, right? One is fit the model. Data with model is not same as test the model prediction. They're not always same. Okay, they're not really same at all, right? So when we try to make connection between data and model, there are many different ways we can pose the question. Okay, and although we started off with saying fit data to the model, what we actually ended up doing was testing prediction of the model about a quantity or about relationship between two quantities. That's what we actually did in this example. Is that right? Did we actually fit the data to model technically? We didn't do. No, we parameterized when the model was adopted and parameterized in that case of the paper I showed you. But it was technically not a fitting. But tell me now, what else can we do about model and data? So one approach is test predictions. Is there anything else one can do? About some quantity. Okay. To be more precise, in the exact example above, we made predictions about a group level problem. What else can one do? There's one more thing, you must always keep in mind, models have assumptions, right? How about testing assumptions? Isn't this another important thing to do? Okay, and that is often much more difficult. Okay. So anyway, so what I will now do is, after this brief discussion, let me now give you a short assignment. Okay. So I'm going to now mention two very simple models. Okay. And the model one is something we have already discussed, by the way. Okay. So, but let me make a connection to the question we just studied. So remember, in this experimental system, there was this angular, arena, right? And animals could go in this direction or this direction, one of the two directions. Okay. Let's call the two directions, two angular directions, A and B. Okay. So let us also, or maybe we can even say, A and B are fine. Okay. So let us denote XA to mean that an individual is moving A direction. Okay. Individual is moving B direction. Okay. Now, let's say you now want to model this behavior that is studied in that example using a much simpler model, even simpler model than what we checked it. Okay. So now, what is interesting about simple about this? There are only two directions to move, right? A and B, right? So, and we are only interested in that quantity phi, which measures whether the individuals are moving in A or B. If everybody is moving in A, that number will be 1. If everybody is moving in B, number will be -1. Okay. So which means we just need to track how many are going in A, how many are in direction A, direction B. Okay. As long as we know, we are done. Right? That's very easy. So let's make some simple routes. Okay. Let's call first rule a stochastic term. What that means is that an individual going in A just decides to change the direction with some rate S. Likewise, an individual moving in B decides to change the direction. Is that fine? This is one rule. Let us now do one more rule, which talks about, which tries to represent interactions between individuals. Okay. What does Vijek model assume? The model that we discussed last time, both Vijek and Cousin model, they assume the following, right? They assume that you look at a neighborhood around you, and then you copy the average of the direction of the neighbors. Okay. Now that is something else. That is it a simple rule or is it a complex rule, according to you? Moving in the average of the neighbors. So what in that case, what that would mean is that an individual going in the direction A, okay, and see how many. Hello, can you hear me?
Yes, we can.
Hello. So an individual moving A will look at the neighborhood and look at the average of other individuals. Let's say 5 of them are moving this way and 4 of them are going this way. It will do an average of all of them and move in that average direction, whatever that average we define. Okay. So, but is it a simple rule or is it a complex rule? Is it possible to simplify it even further?
So here we just have two directions. That would be a simple one then.
To consider Vijek rule as a simple rule here.
So because the number of directions are only 2 Uh,
Okay.
so there is not much randomness or say a variability in that case.
Okay.
Can't we just go with clockwise and anti-clockwise,
As in,
like the movement,
uh-huh.
clockwise and anti-clockwise?
Yeah, so individuals are going in clockwise and anti-clockwise. Okay, so now we have written a stochastic turning rule, which is where they just spontaneously change the direction. Okay, because animals do stochastic things, random things, so it's a reasonable thing to us. But I want to include interaction rules among individuals. That's how will I include this? Simple way.
By taking the frequency of the immediate group, perhaps,
Okay, I've taken the frequency of the
like
direction of the neighbors. Is that what you mean?
the immediate neighbors.
That is same as Vichek rule. No, actually, that would be same as what the Vichek was trying to do. That's one possibility. Let me propose a simpler rule. So when you implement Vichek rule, if you look at immediate neighbor and take the neighbor frequency, how many individuals could be there in your neighborhood? 1, 2, or many? How many would that be? It depends on the density of the organisms, right? If the density is very high, we'll have a large number of neighbors. The density is very low, we'll have a very small number of neighbors. It's a density dependent, right? So let us do a simpler rule here. What I call a pairwise, copy. Okay. So what that means is that an individual A, if you interact with an individual B, you will just copy that fellow's behavior. Okay. So two individuals interact at some rate C and they become same. And of course, the reverse could also happen. XB could meet XA and they both continue direction. Okay. This is called pair, let's call this pairwise copying. And in fact, this exactly same set of rules I have already described in another context. You remember I described a model called binary choice model. Okay, that is exactly this. Okay. When interaction happens, one of them turn towards the other. That's this remember that this interaction was just two individuals, unlike the Vichek model where you need to interact with many individuals. So we have already done this, and we have also derived mean field model for this, if you remember. Okay. Let me now introduce one more, what I call ternary copying. So ternary copying is this: if an individual A interacts with two individuals at a time. Let's give a different symbol for this. Let's call it H. Okay. In a ternary interaction, if an individual A meets two individuals who are both moving in B direction, what do you think should happen?
The A direction will change to B X.
Right? So this is a reasonable thing to happen, right? Okay. So this is what happens. You can also write this in an opposite way, by the way. 2XA plus XB also become 3XA. Okay. So what's happening is that when an individual now, in addition to pairwise copy, individuals can also interact in a ternary way, in a 3 at a time. And in such a case, one way to put this in words is that a minority turn towards majority. Is that reasonable to say here? Okay, is that reasonable to say? Minority copies the behavior of the majority. Okay. So this is a set of rules I have now defined. Okay. New set of rules. So this is the assignment for today.
I have one question here.
Yes, go ahead.
To what we are saying that they are interacting in what ways?
Can you say that again? What do you mean by what ways?
So how they are interacting. So if we say that XA is interacting with XB, so are they spatially neighbors?
That's an extremely good point. In any of these rules so far, have I introduced space?
Nope.
So this is an agent-based model. This is agent-based, stochastic, but not spatially explicit.
Okay.
So here I have intentionally removed space. Okay. So this is not spatially explicit. Okay. So therefore now, who are these guys? So you just assume random interaction. Random encounters. You assume random encounters. Is that fine? Or it's same as saying mean field, we're a well-mixed system.
Okay. And how can we differentiate between whether a single individual is interacting, say the third one, ternary copying? So there we have XA and 2XP. So how can we differentiate the third one with the second in this case?
This, how do you distinguish this and this?
Yes.
Is that your question? That's a
So if the interactions are random encounters.
So how do you distinguish? Remember that there is a rate for each of them. So this
Okay.
is a self-interaction. This is a pairwise interaction. This is a ternary interaction. They are all happening at different rates.
Okay. Okay. Yes. Yes. Got it.
Are the rules clear now? So let us assume a scenario where S is very, very high. C is medium. This is very large. H is very large. It means that this interaction happens more frequently than this interaction. So on the other hand, if C is very high and if H is very low, this happens very frequently compared to this. Okay. So remember that the frequency of interaction depends on two factors. Okay. Given individuals, they happen at rates H, C, and S. Okay. But the interaction rates themselves depends on the densities. Don't forget that, right? Okay. So both of them matter. H matters and the current densities also matter. The actual reaction rates, the population level interaction rates. Okay. So here is the lab assignment for today. Write the mean field model. Mean field equations for the above model. That's your first part of assignment. Second one is, now there are three parameters, right? S, C, and H. I want you to then look at what happens in various limits. Okay, so consider H is equal to 0 limit, and then tell me if order is possible. Okay, that's the first question. Consider H, which basically means that if we had only stochastic turn and the pairwise copy under the mean field limit, can you tell me and H equal to 0 is order possible, and then H is non-zero, again order possible. That is what I would like you to do. Now, what is order? Let us define order as the following. Okay. It's A, it's B, where XA is the proportion of individuals in direction A, XB is proportion of individuals in direction B. Is that clear? So as you can see, if XA is equal to XB, M is equal to 0, meaning there is no order. The number of individuals in both the directions are same. M is equal to 1 or minus 1 would be order. Basically, M is, it doesn't have to be strictly 1, large enough, greater than 0, and it's large enough will be order. That's fine. That's our assignment for it. Okay. So this is you can think of it as a non-spatial model of collective behavior. This collective behavior could be motion if you are interpreting A and B as two directions. This collective behavior could be honeybees choosing between two nests and deciding to go which of the two nests. Okay. So collective behavior could be a choice and where they are arriving at a consensus. Okay, and so on. Okay, it could also be humans choosing between political party A and B, and where they have some probabilities and rates of switching between their opinions about the political parties, and A and B could be opinion about two types of shirts, where my decision on buying a shirt depends on what other individuals are. So it could be anything. So A and B are two possible things that individuals can choose. So broadly, you can think of it as a binary choice. Choice could be direction, opinion of anything. Decision about home, nests, whatever. Okay. And therefore, this type of models are also called opinion dynamic models in the broader context. Okay. Any questions?
So I just want to confirm. So X goes to XB with probability S and remains in XA with 1 minus S.
Wait.
Okay.
That's not a problem.
Okay, thank you.
Okay, now if you are totally confused, what you should do is in one of the lectures, we had actually done a binary choice with only these two. Okay, so I think I had worked out in the class the mean field model for this. Okay, so what you basically need to do is write down an equation for, also distinguish capital XA versus small xa. Small xa stands for the proportions, capital XA stands for the individuals. Okay, so write down equation for small xa, xa dot, xp dot, and then you write down an equation for m dot. That's what you need to do. You should revise how we did for this stuff. I think it's in one of the classes. I can even try to see where. I don't remember immediately. We can find out. But before that, you should revise that and then do this. Okay? To make it a bit easy for you. And then after you have done this, the third question for you is, if someone gives you data, can you distinguish purely, can you distinguish a pairwise dominant versus ternary dominant behavior? So this is a qualitative answer, and basically what quantity will you plot to distinguish that? Any questions, doubts? So I think, if there are no doubts, let's just go back and see where did we do this. Huh? This is reaction diffusion, no. Spatial stochastic model. Okay, maybe in this class. This is stochastic depth. This is 9 was also. Look at this binary choice model. So go to class 9, page 3. I have already showed you. I use the notation A and B instead of XA, XB, but that apart, I have already shown what is, and the notations are different. Okay, so you still have to think through. That's great. But I think, I have already done the basic binary choice with copy. Okay, So you will be basically incorporating pairwise to this. So go to class 9, page 3 to revise how I did, how I should do. And then you will use for this. Okay. Any doubts? Okay. So before I close, I just want to have a quick discussion on how you are all doing on the project. Are you really struggling, or is it clear what you need to do? Because this is a good time to sort of make sure it's all fine. Tentatively, I want to have the final presentation of this one on November 27th, Saturday, 2 to 5 p.m. Okay. We could do it on 26th or 27th. I will confirm closer to the date. Okay. If it's done the first thing as the semester ends. Okay. That's the plan for the projects. Is that fine? So please, block these 2 dates. Now, you can ask me any doubts you have about the progress on project. If you are confused, what you need to do. So I had said that by the end of October, it will be good to update your progress. I was thinking that could happen today, but I did not announce it. And I also thought that because of the assignment extensions and all, maybe you haven't done it at all. So we will see how to do that. But any broad questions on any concerns about the project progress? No?
By the time we will be presenting our final results, so do we need to submit also a report along with that?
That's a good point. Presentation, just a 3-page report, okay? Because I won't have time to read for like 20 pages. The 3-page, on a regular 11 point, one line spacing, okay? Standard format. Maximum 3 pages, could be shorter. Is that fine? If we're done and out of the way of this course by the end of November last week, and then you can focus on other exams. Okay. So now, if there are no questions from your side, so I was thinking of 2 possibilities. One, make the presentation, and so maybe it's actually better to do the following. I will do the following. So I will give you a deadline. Maybe I'll give you a very short deadline. I don't want you to spend too much time on it. So maybe sometime next week, I will ask you to submit a 1 to 1.5 page report where you will modify your previous, whatever you had given me as your proposal for your work, okay, and then update that to include the current status. For example, you must tell me. So I'm going to assume that in broadly, whatever the problem you have chosen, right? Your problem should have a model, right? Your problem, the statement must be very clear. You must explain that in 2 paragraphs, and then now I would try to make sure you now have a model that you are working on. What is the model? Have you finalized your model? Because if your model is not final by now, you will not have time to address your question. Okay. So what I'm hoping is that in your report you will address this part. What is the model? Is that fine? No. Now you had said also when your previous proposal on the project, you had said some of you had 5 questions that you were saying in that. Okay. Now narrow it down, filter it to focus on what you think is most important, reduce them. But you must also now have a model that you have finalized to work on. Okay. And then tell me the status of implementation of your. So I can just write down 1.5 page report. So this report will be useful for you because you can then expand to make 3-page report when you have 2 to 3 paragraphs that has background plus question statement, and then So whether the model is developed by you, you're adopting somebody else's model is totally irrelevant to me. I just want to make sure we have the model. Okay, and then quickly next steps, in bullet points, could be the bullet points. Okay, this is what I would need. Today is 29th October. The November 2nd deadline do for you. November 3rd is also fine. Actually, I won't be able to evaluate quickly next week, but I want to submit. Is that fine? Okay, I'm going to assume that to be a fine, because there is no response. So the point is that I want to make sure you have done